Artificial intelligence is eating the world. Companies and nations alike are in a race to scale the production of intelligence.
The plan so far has been simple. Scale the same old computing paradigm by feeding it more data and more power. A lot more power.
Data center providers are going as far as building their own nuclear power plants, looking to achieve an energy supply that is poised to dwarf the current US energy grid several times over. But simply pouring more power into the current compute stack will be far too slow and too costly to produce human-level intelligence and distribute it to the world. But scaling energy is only half the equation. The other part is about how efficiently we can turn that energy into intelligence.
What if, instead of simply scaling power production, we increased how many thoughts we can generate per watt?
What if we reimagined the density of intelligence we can achieve in matter? We'd need to fundamentally rethink the hardware layer from the bottom up. Luckily, nature has already shown us that a far greater energy efficiency is possible. We can take inspiration from its underlying physical principles and harness them directly in hardware. That's why at Extropic, we're building a new kind of device, a probabilistic computer for a new era of computation, along with new algorithms that can be run on them.
Extropic's computers feature new types of computational primitives that sample from simple probability distributions. And it turns out if you combine many of these sampling circuits together using some concepts from machine learning, you can actually build a system that does kind of the same fundamental task as something like ChatGPT or Midjourney.
At the core of our devices lie new computational building blocks, which sample from simple probability distributions. One of our core primitives is called the probabilistic bit, or p-bit. Instead of simply being a 0 or a 1, a p-bit can be tuned to flicker in between, spending time in each state according to a programmable probability.
When you connect millions of these p-bits together, immense computational power can emerge.
We call these new types of processors thermodynamic sampling units, or TSUs.
And today, we're unveiling our first step towards scalable TSUs with X0, our first prototype silicon chip. Our X0 prototype is a simple device comprised of dozens of probabilistic circuits, demonstrates a set of novel primitives, and proves that these primitives can be reliably built and controlled in silicon and at room temperature.
And for the first time, we're making TSUs available to early users with our testing and prototyping kit called the XTR0. This desktop device hosts 2 X0 chips, letting researchers explore hybrid algorithms that combine traditional processors with thermodynamic sampling units.
XTR0 will be available to select early access partnering organizations this fall.
Alongside XTR0, we're open sourcing Thermal, a Python library for simulating TSUs on GPUs. Thermal allows developers to start building algorithms today that will run efficiently on tomorrow's thermodynamic hardware. We're excited to collaborate with the open source community to kickstart explorations of the Thermo AI algorithmic landscape.
And last but not least, we're announcing our next generation TSU, Z1. Z1 is our first commercial scale TSU and will feature 250,000 interconnected p-bits per chip, forming a large programmable graph.
Z1 chips will be integrated into systems comprised of millions of p-bits, unlocking the potential of thermodynamic computing while maintaining a power-efficient and dense form factor.
Z1 is important because you can use it to run energy-based models, which are a type of machine learning model that serve the same fundamental purpose as today's transformers or diffusion models, modeling complicated probability distributions.
Today, we released our first paper where we talk about denoising thermodynamic models,
which are a new type of machine learning model that we developed here at Extropic to leverage our thermodynamic sampling units most efficiently. In the research presented in the paper, we find by simulating a small piece of a Z1 TSU that we can solve simple generative modeling benchmarks using around 10,000 times less energy than the most efficient algorithm running on a GPU.
At Extropic, we're charting a new path forward for artificial intelligence. In just a few short years, we've moved from concept to room-scale cryogenic experiments to a desktop prototype that runs at room temperature.
We've designed and built new probabilistic primitives that form the foundation for a whole new era of computing.
We believe that thermodynamic computing will fundamentally redefine how we convert energy into intelligence.
If you want to help us pioneer this paradigm, join us.
The journey will be long, but the payoff for densifying intelligence will be immense. Extropic, building the ultimate substrate for intelligence.